Welcome back, everyone. So we introduced this concept of partial pressures in the previous two videos. We said that the sum of the pressures from the individual gas molecules, their identity, can be summed to get the total pressure of a system. And so the partial pressure is that pressure associated with that particular gas species. In the last video, we did an example of calculating partial pressures using the ideal gas law. We can also calculate partial pressures if we know something about the mole fraction of that substance in a mixture. Mole fraction, just as the name sounds like, mole fraction is essentially a fraction of the number of moles of that species divided by the total number of moles in your system. So if I, for gas molecule A, to find the mole fraction of A, I need to know how many moles of A I have divided by the total number of moles in that system. So with mole fraction data along with total pressure data, that is another way that you can calculate the partial pressure of a species in a mixture. So in this next example, we're going to take advantage of those two examples to do this example. It's also, I believe, there's one like it in your MindTap. So let's go ahead and do this one. So I've got a mixture. I'm reading this problem. I have a synthetic atmosphere. So I've got a mixture of three different gases: carbon dioxide, oxygen, and argon. And I know their mole percents. Their mole percents. I need to calculate the partial pressure of oxygen if I know the total pressure of the system. And then I need to figure out how many moles of oxygen are needed in that atmosphere if I have a particular volume and a particular temperature. So let's tackle this first, obviously tackle A first, and let's address these mole percents and how they're going to be useful to us. So we know that the total pressure of the system is equal to the sum of the pressures of those three components. This problem part A wants us to calculate the partial pressure of oxygen. Well, the partial pressure of oxygen is going to be the total pressure of the system, which we were given, 745 torr, multiplied by the mole fraction of oxygen. I didn't give you the mole fraction, but I did give you a percent. So we can think about that percent as like a fraction. So if we think of a sample, this sample is 100%. My total mole percent is 100. Then 18 moles of it, or 18%, is due to oxygen. So I can take my mole percents and put them as a decimal and use that as my mole fraction. So the mole fraction of oxygen in this atmosphere is 0.18. If they had asked me about argon, I would have said 0.805 is my mole fraction. The mole fraction of carbon dioxide would be 0.015. Okay, so changing those mole percents into fractions, just divide by 100. So I know my mole fraction, I know my total pressure, so I can just multiply them to get the pressure, the partial pressure of the oxygen. So that's how do you do the first problem. Now I want to know how many moles of oxygen are needed for this. Well, I've got a pressure of oxygen in torr, I've got a volume, I've got a temperature. I can go ahead and solve for N using good old Pivnert, making sure that I use the appropriate pressure in atmospheres and the appropriate temperature and volume in liters and Kelvin. And so doing that, converting that 134 torr into atmospheres and setting up PV equals nRT, I see my units cancel appropriately. That leaves me with a final answer of 0.080 moles of oxygen. So, mole fraction equal to the number of moles of that species divided by the total number of moles in your mixture. Mole fractions can also be used in conjunction with the total pressure of a system to find the partial pressure of that component.